Okay, following is the theory behind unbreakable two-way encryption that I call AKASHIC encryption. Before I get started, I have to dispel a couple of myths. There's a myth out there that any encryption can be broken. That's false. Encryption can be broken if there is some means of telling whatever cipher you're using is on the right track, and you have enough time and enough computing power. But there's another kind of encryption where you can go through every combination and every cipher, and you'll eventually find the correct one, but you have no means of knowing which one it is. So you're actually just guessing at what the data is. So encryption can be unbreakable. The other one is that it requires a genius, or it has to be super complex in order for it to be effective. It's not true at all. It doesn't take a genius to make what would take a genius to break, and in this case, it doesn't matter how many computers you have or how much time you got, it is not possible to break this kind of encryption. This encryption is ideally suited for two-way communication. You would not use it for like file storage or anything like that. There is certain technologies like with drones and things of that nature where you need two-way communication, and it has to be unbreakable. There can't be any security breaches whatsoever. So, how do we do that? Well, first you need a key. A key is basically just data that's totally random. And before you say it's impossible to get random information off of a computer, you're not correct. So what you do is you want to seed the random generation. How you do that is person presses a key on the keyboard, and at that same time they press a key, a snapshot of the processor timer is saved, and in this case it's all the way out to nanoseconds. Alright, so you're going to take the key that they pressed and the last character, or the last digit of the nanosecond portion of the CPU timer. The reason why you go with that one is it's impossible to, even if you're holding a key down, to have this be like one digit right after another, after another, after another. With all the other processes going on the computer, even if you had a real-time operating system and you held a key down, it would still be very different. They call that timer drift. Okay, so you add those two values together. And this is how we do it. Now, in the real world, we use the ASCII character set, which is 256 characters. But for the case of this tutorial, I'm only going to use just A through Z and just assign values therefore. So like A is 1, blah, 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 blah. You get all the way down to Z, and let's say you add another value, it goes back around, so it's 27, so 26, 27, yada, yada, yada. Alright, so in this case, user seeded this by hitting a couple different keys. It added them together, so it took the value of O, which is 15, added the digit here, 6, and that's 21, and of course if you look up 21, it is U. Not U, but the letter U. Alright, so you do that for everything, but what happens when you get a number that is not in your character set? Like, you had 22 plus 9 was 31. 31, it stops there. Okay, well, that's why I flipped it around. Went 26, 27, 28, 29, 30, 31. And that, I call it character flipping. Here's the formula for how to do that. We're taking the character that we want to get, the combination character, and this is the character, our input character. In this case it would be 31. L, this is the length of the character set, so there's 26 characters here. With ASCII it'd be 256. And you're going to, you have to solve this in here. You take the character value and add 0.1. This is just trust me, you have to do it. Divided by the length of the character set, and you get the integer portion of that number only. That's just a fancy way of saying anything after the decimal point, ignore. Don't round up, don't round out, down, just strip it off completely. And anyway, in this example, I showed how taking 31 would play out, and lo and behold, it's number 5, which is E, which is what I got there, and that's 31. Alright, moving on. So this is how you create a random key, or how you seed a random key. As you can see, these would be the bytes that would start out the key, but the rest of the key can be filled up by the process taking a snapshot of the timer, using that to seed a random number generator, blah, blah, blah. Basically, you can continue making random data. It's just you want to seed it with real random data first before you do that. So now you have this big random key right here, randata. Just pretend that's actually random. You take the key and you give it to two people. Well, yourself, and you share it with someone else. Preferably you do that in a secured method, like face-to-face. If you want to use some sort of open SSL encryption, if you actually trust them, go right ahead. But anyway, so you both have the key. Now I want to send this word to them. I want to send the word text, alright? So I add R, which is the first part of my key, plus T, which is the first character here. So R is 18, T is 20, so that's 38, which is L right here, 38. And that's what we got. So you add the byte from the key to the byte from the text, and you get a new encrypted text. Alright, so that's the first part, but we're going to want to replace what we just used in our key so that we can use it again without compromising our security. So since that was 4 bytes long, we're going to create a new key that's 4 bytes long. So we take the random data generator, and you don't have to push keys or anything. It can create its own random data just continuously. And anyway, it gives you 4 shiny new random bytes. Alright? So I'm going to send the encrypted text that I just did, plus I'm going to encrypt the random data that's going to take the place of that part of the key. So I add D to Z, blah, 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 and sure enough, we get this whole encrypted string here that's exactly twice the size of the unencrypted string. Okay, so now our new key, we're going to take the ZYDB, that's going to be the start of the new key that replaced what we used here. But on the other end, they don't know that. They don't know what that key, that replacement section is, but they can find it out. So they received this encrypted string right here. They take, instead of adding the byte from the key to the byte from the text, we're now going to be subtracting, we're going to subtract the key byte from there. So L minus R. Okay, L is, let's see, where is it? Okay. We're going to use 38 minus R, which we're going to use 18. So that's 20, and 20 is T, first part of our unencrypted text. Alright, so you do that same process, and you get all the unencrypted text here. You do the same thing, and you get the unencrypted section of key that you're going to now put here. So you now have the unencrypted text, or the decrypted text, and you both share the same key again. The reason why this is unbreakable, they can go through every single combination of characters here, and eventually they'll come across the right one. The problem is, there's no way for them to verify when they have the correct text here, because the section key that you use to replace it is completely random. So was the section that was originally created that encrypted that section. There's no special math formula or anything fancy. It's just one-to-one replacement. The only way this could be cracked is if they had the key to begin with, which that's not really cracking at that point, that's spying. which case they really wouldn't have to do much decryption because they would already have your data. Anyway, so that's what makes it unbreakable. It's also what makes it very simple. And unlike my other tutorials, I am actually going to be including the source code for a basic app to do just this to files. I'm not going to get too fancy with it because I know programmers will just rewrite it anyway and make it however they want. So it's just a very basic program. And that will be in the project files link. So that is all.